All right, question number 57. Dextrorotatory compounds rotate plane polarized light to the right, to the right. Levorotatory, rotate plane polarized light to the left. Okay, so you should know the whole concept of plane polarized light being rotated by a chiral compound. If it rotates it to the right, that's considered dextrorotatory, and if it rotates it to the left, that's considered levorotatory. The drugs in question 58, the drugs Prilosec and Nexium both contain the same active ingredient. Nexium contains a single enantiomer, but Prilosec is a racemic mixture. Which drug would be more effective if you got a 20 milligram dose? Well, if you took Nexium and you take 20 milligrams, if it's only got one enantiomer, you end up with 20 milligrams of the effective drug. Whereas if you take Prilosec, and if you take 20 milligrams of it, since it's a 50-50 mixture, right, one half is going to be the active ingredient, the other half, the other enantiomer, is going to be inactive, right? So you're only ending up with 10 milligrams of the active product. And so Nexium is twice as effective as Prilosec. Number 59, I wouldn't expect you to have this one memorized and be able to just spit this back out at me or anything. But it just says, how many different triose sugars are there? I'll just kind of go over them with you, what they are. Everybody should know what glyceraldehyde is, okay? So glyceraldehyde is this molecule here. We looked at it, Avogadro's number of times. This is glyceraldehyde. If you switch the stereochemistry, here if you reverse the hydroxyl and the hydrogen, you end up with L-glyceraldehyde. And there's one more, and that's dihydroxyacetone, which is this compound here. Okay, and you would have heard me mention dihydroxyacetone a few times. Dihydroxyacetone. Anyhow, all of these compounds have the same molecular formula, and they're all considered triose sugars. Again, I wouldn't expect you to be able to regurgitate that at me or whatever, but I do expect you to know what D and L-glyceraldehyde are. All right, number 60. How many chiral carbons are present in the straight chain form of glucose? What about the cyclic ring? This is a good question. I don't know if it's something that you've ever thought about, but if we draw the straight chain form of glucose, which looks like this. No, sorry, I made a mistake here. There we go, that's more like it. Okay, if we draw the straight chain form of glucose, you can see that there are actually 1, 2, 3, 4 chiral centers in the molecule. However, if we draw the cyclic form, and we can just draw the, we'll draw the alpha just for fun. So it's going to look like this. We see that there are only 1, 2, 3, 4, and then we have a fifth chiral carbon up here. Oops, am I missing one here? So in the first one, we have 4 chiral centers, or 4 chiral carbons. And then in this form, the closed ring form, we have 5 chiral carbons. So let me fix something here. All right. Here we go. Number 61. Is the following structure alpha or beta D glucose? I'll just throw that out there to my students. Could anybody tell me, is this molecule alpha or beta D glucose? And it's not a trick. Yeah, thanks, Gavin. It is alpha, because hydroxyl at anomeric carbon is pointing down. Number 62, the two simplest sugars are glyceraldehyde and dihydroxyacetone. We looked at those a few minutes ago. Dihydroxyacetone does not rotate the angle of plane polarized light. If we draw a molecule of dihydroxyacetone, it doesn't rotate plane polarized light. And the reason why is it has no chiral carbons, does it? Chiral carbons. There are no carbons in the molecule that have 4 different things attached to them, do they? Nothing. Okay, so dihydroxyacetone has no chiral centers. Number 63, a glycosidic bond occurs when a blank functional group of one sugar reacts with a blank functional group on another sugar. So it's simply when the hydroxyl or the OH functional group on one sugar reacts with a hydroxyl on another sugar. Hydroxyl, there we go. So the hydroxyl, let's say on, carbon 1 reacts with the hydroxyl on carbon 4, and you form either an alpha 1,4 glycosidic bond or a beta 1,4 glycosidic bond, right? Alpha 1,4, we see that in amylose. Beta 1,4, we see that in cellulose. We talked about those in quite a bit of detail. Next one, it says, draw a reaction which results in trans fatty acids in processed foods. Well, if you have a fatty acid, okay, a naturally occurring fatty acid, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something like that, 12, okay? This is a cis fatty acid, and naturally occurring fatty acids are cis fatty acid. But what happens is sometimes when you try to hydrogenate these, instead of undergoing hydrogenation, they'll undergo isomerization. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12. And you go from the cis to the trans, like that. So you just end up doing an isomerization instead of a hydrogenation. And that's where trans fats come from. Trans fats are unnatural, right? They're produced from the hydrogenation of naturally occurring unsaturated fats. And they're linked to, coronary artery disease and atherosclerosis. So there you have that. All right. Number 65, an alpha 1,4 glycosidic bond is found in what types of molecules in plants? So we would find that in amylose, which is found in starch. So amylose, so we'll put in starch. All right, it's not found in cellulose because the beta 1,4 glycosidic bond is found in cellulose, which is also found in plants, but it's not alpha, it's beta. Name 3 roles of lipids. I don't know. We can see here. Shock absorption, insulation, cell wall structure, energy. Let's put energy. Cell wall structure. Synthesis of biomolecules. I put here hormone production, for example. Hormone production. We can put insulation. Animals use fat as insulation. What are the components of a triglyceride? what type of functional group links these components together? Well, everybody should know that a triglyceride is made from glycerol. So you should be able to draw a molecule of glycerol, and then you react it with 3 equivalents of a fatty acid. Okay, and then you end up making a triglyceride. And in a triglyceride, we have 3 ester bonds. Triglyceride. Okay, so what type of bonds link these components together? These are esters, ester linkage. So glycerol and fatty acids held together by ester bonds to make a triglyceride. Triglyceride. Stearic acid is very common in both plant and animal tissues, while oleic acid is much more common in plant tissues. How does oleic acid differ from stearic acid? Now, if you look at my solutions that I posted to Brightspace D2L, I have the whole structures here. So stearic acid has a total of 18 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Stearic acid. So it's a saturated fat, right? Saturated fatty acid because it comes from an animal. And oleic acid is just an unsaturated fat. I'm not going to write out the structure, but I'll put here oleic acid has a double bond in it. So it's an unsaturated fatty acid. All right, there we go. Describe the structure of phosphatidylcholine. So phosphatidylcholine, what class of lipid is it? And what role does it serve in the body? So phosphatidylcholine is a phospholipid. If we look at the structure of phosphatidylcholine, we have the glycerol backbone. We have 2 fatty acid residues attached to it. I hope I don't run out of room here. Then you have the phosphate ester portion here. Okay. And then you have this little molecule called choline tacked on the end like that. So a phospholipid. So where do you find a phospholipid? It's going to be found in cell membranes. Found in cell membranes, right? When you look at the phospholipid bilayer, you always talk about the polar head group, which should be this portion here. And then you have the 2 fatty acid tails, which would be this portion here. I'm not going to draw the fatty acid tails out right now. Yeah, so that's enough. Found in cell membranes, that's good enough for me. Draw the straight chain form of D-allose, a C3 epimer of D-glucose, then draw the correct ring form of this molecule. So I always start it with glucose. So something I've never told you, but it's a good idea to have the structure of glucose memorized. Why? It just comes up so dang much in organic chemistry. Now, the way that I do it is I always think of 134. And what does 134 have to do with anything? If I think of these carbons here, or these bonds as being 1, 2, 3, 4, on carbon 1, 3, and 4, I have a hydroxyl. So all I have to do is fill out the rest. I have a hydrogen here, and then everything is the opposite on this side. So this is D-glucose. D-glucose. So what's a C3 epimer? All that means is if this is carbon 1, 2, 3, all I have to do is flip the stereochemistry at carbon number 3, and that gives me an epimer. Okay, just inverting the stereochemistry at one stereocenter. So if I copy this molecule, just to save a little bit of time, I'll paste it right here. Okay, so all I have to do is flip that one part of the molecule, and I end up with a hydroxyl over here and a hydrogen here. So you can see that everything is on the same side of the molecule. So that means that all of those hydroxyls are going to be pointing down in my Haworth representation. So the correct alpha ring form. Okay, well, if it's alpha and it's the ring, we're going to start by drawing the ring. We have the oxygen in the top right-hand corner. We have CH2OH up here. It's telling us that it's an alpha, so that means the hydroxyl is going to be pointing down. This is carbon 2, this is carbon 3, this is carbon 4. 2, 3, 4. Every single one of those hydroxyls is going to be pointing down, down, and down, like that. And so what we have drawn here is the straight chain form of diallose, and then we have the Haworth projection of alpha diallose, because the anomeric carbon is pointing down, the hydroxyl on it, is pointing down, which renders it alpha. All right, reducing sugars and non-reducing sugars. So a reducing sugar is going to be one that doesn't have anything attached to the hydroxyl at the anomeric carbon, and a non-reducing sugar is going to be one that's part of a glycoside. So if you have, let's say, a ring like this, okay, as long as this hydroxyl is free, it's a reducing sugar. So let's just draw the allose that we had here. So free hydroxyl, free OH at anomeric carbon equals reducing sugar. When there's something attached to it, however, it is a non-reducing sugar. So if I copy this, and I paste it over here, if you were to put a substituent on there, like an R group, like this, then it's non-reducing. Simple as that. Glycogen is very similar to what other material? It's very similar to amylopectin. What's the difference? Is that glycogen has shorter branches that are more frequent. Glycogen has shorter, more frequent branching, like that. Why are lipids insoluble in water? Well, hopefully you could give me a little bit of a reason as to why. It's because they're nonpolar, right? They are nonpolar molecules. Made up of mostly carbon-carbon and carbon-hydrogen bonds, which are nonpolar. Right? Water is polar, and you remember the rule, like dissolves like, and since they are not alike, they're not going to be soluble, one in the other. What polyalcohol is a component of all triglycerides? Give its common and IUPAC name, and I expect you to know this by now. It's glycerol. So if you draw out the structure of glycerol, the common name is glycerol. The longest carbon chain has 3 carbons in it, so this is some kind of propane, right? And you have a hydroxyl group at carbons 1, 2, and 3, so this would be 1, 2, 3, propane, triol. There's another way you could name this. You could call it 1,2,3-trihydroxypropane as well. So, or 1,2,3-trihydroxypropane. That works too. What is the number of carbon atoms in an alpha amino acid? There's only 2. You should be able to draw NCC. You should be able to draw the C terminus or terminal, the N terminus. We have the hydrogen here and an R group, so we have a total of 1, 2 carbons in an alpha amino acid. From the list of the amino acids below, identify the structures. Look, I don't expect you to memorize any of the amino acids. However, I do have some students who expressed an interest in learning them. So if you're the kind of person that wants to memorize them, maybe for another class in the future, be my guest. I think it's never a bad idea. When you just have a methyl group like that, that's an alanine. Okay. If you have the methyl and then you've got a phenyl group attached to it, that's going to be phenylalanine. When you have a sulfur, this is cysteine. So cysteine. And then when you have this hydroxyl here, this is serine. Again, I don't ask you to memorize those. It's more just a fun thing. The next question is just a little bit of lesson in German. What is a Zvita Ion? Okay, it's just a compound that's got more than one charge in the same compound. So we'll put here a molecule with both a positive and a negative charge. And what would be an example? An amino acid, a physiological pH. So I'll draw a bond line structure of an amino acid like that. So that's a Zvita ion. We've got the cation and the anion present in the same molecule. Draw the structure of the amino acid below. So this is lysine, which is a basic amino acid. If you were at a pH of 1, a pH of 1 is very acidic. Okay, that's super strong acid. So what's going to happen when I treat this with really strong acid and I put it at a pH of 1.0? Since the two amino groups are basic, they're going to take on protons, aren't they? But the carboxyl group is going to be unaffected. So I'm going to have NH3 plus here, and I'm going to have NH3 plus over here. Okay, the two amino groups or basic groups are going to be protonated. How many amino acids have acidic side chains? There's only 2 of them. Aspartate. Aspartate and glutamate, or aspartic acid and glutamic acid. So aspartic acid, which the conjugate base is aspartate, which is this. And then glutamic acid or glutamate. Glutamic acid. Let's move on. What time is it? We don't have a lot of time left. Draw the hydrolysis of Alanyl phenylalanine. So let me show you. I have NCC, because I have 2 amino acids. It goes NC-carbonyl. The C terminus will be a carboxylate. The N terminus is protonated. I have a hydrogen here. I have a hydrogen here. I have a hydrogen here. The R group of alanine is a methyl group. The R group of phenylalanine is a CH2 followed by an aromatic ring. What are we doing? We're going to hydrolyze that in water. So we're going to break the amide bond, which is this bond right here. This is the amide bond. So we're going to cleave that bond. Then we're going to end up with the alanine molecule. So this is the alanine. And then we're also going to end up with the phenylalanine. And there we go. And there you have it, folks.